Excellent. Okay, so my name is Jorge. I'm from the University of Illinois, Urbana-Champaign, and I'm here representing the program, The Many Faces of Relativistic Fluid Dynamics, which is going on now until more or less the middle of July. And the title of the talk is Relativistic Fluids from Particle Colliders to Neutron Star Mergers. So this is my first time at KITP, and this is really, truly an amazing place, and there's an amazing view. And I think if you take into account also the fantastic Munger residence, this has got to be the institute with the largest number of pianos per scientist. So it's really amazing. I'm one of the coordinators of this program, and we are very invested in this. In fact, my daughter was the one who drew the mascot for the program, which is a little Einstein swimming in some, I guess, in relativistic fluid with some cube or something. Take a look. So today I'll tell you why we're excited about fluids in general, and especially relativistic fluids, and how the most complex, like one of truly the most complex scientific apparatuses ever created by humans, like the LHC and LIGO, why this type of experiment, or these experiments, are actually forcing us to rethink what actually constitutes fluids or fluid dynamics in general, especially in the relativistic regime. So the questions that you see here, of course, they're part of the program, but you see that some of these questions are actually bigger than just a single, they cannot really be addressed by just a single community alone. So that's why in our program we have many different types of people. We have nuclear physicists, particle physicists, string theorists, mathematicians, people that do numerical simulations of fluid dynamics, also in numerical relativity, and other different types of people. So let me start with one fundamental thing, which is this. In this talk, the following natural units will be used, because otherwise you'll be confused, especially if you work with condensed matter with systems where this is not a useful system of coordinates. So let me start with the first question. So you see, throughout this talk, I'm going to lay out a few of the fundamental questions that motivated all these people to get together and create this program. So one of the questions, and I think you all probably share the idea why this is so interesting, is this. Why are fluids so ubiquitous in nature? Right? So in fact, if you think about it, and there are many people that work in different areas here, people use fluid dynamics, or when they're solving some equations, you see that the actual dynamics looks like a fluid, but in very, very different scales. Very, very, very different. So, for example, cosmological scales, when people study the structure, large-scale structure formation of the universe, there are also simulations at galactic scales, and also, this is something more recent, simulations of the plasma surrounding supermassive black holes. So supermassive black holes, this is the H. For example, the one in our own Milky Way, which is Sag A star, right? So this, and people actually use fluid dynamic simulations for this. These are talking about length scales of the order of 10 to the 10 meters. Okay. So, of course, if you keep going down, you end up with stars. And for me, I'm interested in neutron stars and neutron star mergers, which have been spectacularly been measured since 2017. And then here, of course, we're talking about fluid dynamics at the scale of the order of 10 to the 4 meters, because the radius of a neutron star is like 10 kilometers. And of course, you can keep going down to the human scale, like the air around us, and even further and further, for example, for nanofluids, it's something that a lot of people work on. So, but why? Why can we find so many examples where fluids become useful? It's a good description of certain phenomena. So I think that The answer could be complicated, but I think there is a phrase that I think is useful, which is the following: is that nature can produce complex structures even in very simple situations, and also can obey very simple laws, even in the most complex situations. And you'll see that this talk is about this type of concept. Okay, so this is how this different type of dynamics will show up, especially in the relativistic regime. So, but of course, the first thing you will say is that, why are you worried about this? Or why are you interested in this? We all know everything about fluids, right? In fact, if you're a professor, you may even say, oh, I just taught this last semester, so it's fine. Well, there are several things going on that I think you will see that will motivate why one has to rethink a little bit about what happens to fluids. Indeed, the very first thing that you would think when it comes to fluid dynamics is you would say, oh, fluid dynamics is all about the conservation laws. It's all about the conservation laws. And what I mean by conservation laws here, so we can talk about energy conservation, of course, and momentum conservation, and especially first in the non-relativistic regime, which I'll use as an example. Also, we talk about mass conservation. Okay. And these are obvious concepts that we teach everyday physics. So the energy is conserved. Even for the fluid, you can have some part of the kinetic energy that is converted into heat. So for the momentum, that the fluid cell carries is affected by the stresses that that little cell experiences as it moves through the fluid. And also mass conservation is just that if you have some stuff that is here in this volume, if you wait long enough, maybe some other mass came in, or this mass just came out. So but the mass itself is conserved. Okay. So those are very basic concepts, very basic. So, but this is not enough for fluid dynamics as we normally understand it. There is another important thing, which here I'm going to call locality. And I'm going to explain to you what I mean by this. What I mean is the following. Imagine that you have a fluid. Right? A fluid has many little particles in motion. And what I mean by locality is that the particles are influenced by other particles only in its immediate neighborhood. Okay? So that's very, very important. Because ultimately, there was going to be a technical part called derivative expansion or gradient expansion that will show up precisely because of this assumption. Right? That we are interested in phenomena or systems where this property that I'm calling locality here can be useful. It can be systematically implemented. Cool. Of course, I mean, it doesn't mean that I cannot use fluid dynamics for systems that have some other forces. For example, electromagnetism. Yes, of course, one can do that. But this locality concept that I mean here, I think you got the point. So, and the other part, which sort of connected to this, is the presence of a large separation of scales. And what I mean by that is the following, is that, imagine that you have this air here. Okay? So this air is made of air molecules, and you can associate with the collisions that happen once in a while in these, among these little molecules, you can establish some little scale, some microscopic scale, which I'm going to call little l, which is of the order of the mean-free path of the particles in this gas. Okay? So this would be, for example, something like this, 10 to the minus 7 meters. However, in order to describe how I'm moving my hands here and the air is coming to you like this, we don't need to talk about physics at this scale. It's enough to consider phenomena defined at a much larger scale. Here was the micro, And here is the macro scale, macroscopic scale, which is associated with the gradients, the spatial gradients of conserved quantities. For example, the density of particles here. Okay, so this would be associated with things like this, like the gradient of a density. So, normally we associate with fluid dynamics things where the ratio between the very tiny little microscopic scale and the typical scales associated with the fluid phenomenon that you're describing, the big L, is when this thing here is much smaller than 1. That's normally where fluid dynamics appears. Okay? And this ratio, I'm going to call it the Knudsen number. It's some standard notation that we get from the theory of gases. But it's basically, remember this, when there's a large separation of scales, that's where normally fluid dynamics is supposed to emerge. But yes?
You started off by setting h bar to 1. If h bar was 0, would anything change in your talk?
Yeah. H bar going to 0. Not at this point yet, but yeah, so there is a lot of different phenomena here that only exist because h bar is, I mean, there's some quantum phenomena here, for example, related to confinement. But so far, yeah, this is pretty general.
Can you also comment on the lack of angular momentum conservation?
Oh, yes, no, of course, yes. And in fact, this is a pretty good question here, because, for example, in my field, what people are trying to understand now is to see what is the precise dynamics of angular momentum in the relativistic regime. I know that in the non-relativistic regime, there are several types of interesting systems where you actually have to write down equations for angular momentum. You even have the equivalent of like Navier-Stokes equations for angular momentum. So yeah, so it's systems with internal spin, not really spin, but some internal rotation. You can have that even in classical regime, yes. So yeah, so in principle you would have to put that there too. Okay, so this looks very general, right? And this is the motivation for most of the things that we do, and most of our understanding. So what you see then is that if you put together conservation laws plus this concept of locality and the idea that you have a large separation of scales, okay, if you add to that the standard physics of Newtonian mechanics, you end up with the famous Navier-Stokes equations. And I'm going to write them down here and discuss a few features because they are useful already in the non-relativistic regime, but we're going to see some of its properties. So what happens when we try to write down these things in the relativistic regime? So basically the point is, how do you make sure that all of these big ideas survive or are well defined once you impose that the theory has to be relativistic? So Lorentz invariance is a property, it's a symmetry of your system. So, Navier-Stokes effect. So if you put this together, I think Navier started working on this actually in 1822, so it's like 200 years ago. So this sort of started in 1822. And basically, it's a way, once you say that Newton's laws work, right? So you can have an expression for what it means to talk about velocity and what are the definitions of forces. Then you can just write down what the equations are. And I'm going to write them in full generality. And then I'm going to comment on the other approximation that I'll make soon. So this is just the mass conservation, the continuity equation. So it's a conservation for mass. Okay? So this is a density that varies in space and time, and this is the velocity of the fluid. I have a momentum equation. This is the momentum of a fluid cell, and this is the stress. This is the stress tensor of your system. So it says that you could have momentum changing if the stress has spatial gradients. Okay, so this is momentum conservation. And the other one I'm going to write it down here just to be precise, is something like this. So these equations are common. So this is the equation that will tell you about energy conservation. And what you see, there is a thing here. This is the internal energy density. Okay, so the one associated with heat. This is just a kinetic energy density, and there is a current. So it says that this quantity here varies when this current has some gradients. Okay? So, but with this, if I just state these equations, no one can solve them. Because I have how many variables? I have the density as a variable, I have the velocity, so I have 3 fields here. And I could use, for example, I have a pressure term. I could write the pressure in terms of the density and in terms of the internal energy density, or the pressure in terms of the density and the temperature. So I can use the equation of state, to write down these thermodynamic quantities as I want. So let's say that the variables are density, velocity, and temperature. So I have 5 variables and I have 5 equations. That's great. But I don't know what these things are. What are the shear stress here, or the standard stress tensor, and this energy current? How do I write these things in terms of the other variables? If I don't do that, then I cannot solve. And that's where a lot of the physics comes in, and precisely this notion of locality, the separation of scales. Because with this, I'll be able to write down leading order expressions for these quantities. Okay? So I'm going to write this down. And they look like this. The stress has to be a symmetric tensor. And just like this. Let me write it like that. So first, so imagine that you are in equilibrium, right? So these systems have to be such that no entropy is produced in equilibrium. That tells you that at least this shear, or this stress tensor, has to have a few properties. And here, you see there's another property, symmetry. The symmetry of the equilibrium states tells you that the pressure in equilibrium is isotropic. That's why there's this delta Ij. Okay? And here, this is just the velocities. So if I were to stop here, I would find Euler equation, the equation that describes an ideal fluid without viscosity being produced. This dissipative tensor is the thing that will lead to entropy production, and that's where all these different layers of modeling, symmetries, locality, enter when I write down expressions for this, written in terms of the other variables. So then I can actually solve the equations. So for example, if I want to write this in the following way. So this, oops, something else, right? Got too excited here. So this has to be such that in equilibrium this is 0. So it can only contain expressions that are 0 in equilibrium, but then out of equilibrium they can lead to entropy production and things like this. So here comes the idea related with this Knudsen number, or the expansion in between, what you call macro and what we call microscopic scale. Because to first order, and that, the expression that I can write down looks like this. And you may recognize this from standard books, like the Lipschitz and any other book about fluid dynamics. So this introduces the shear viscosity. It comes with this weird transverse gradient of the flow velocity. And here is the bulk viscosity. So assuming that the system is not incompressible, so this thing here is different than 0. This is the divergence. So there's 2 transport coefficients, eta and zeta. So in general, for you to solve the equation, you need to know how these things here depend on the temperature and the density. So you could do the same idea So this is first order in Knudsen because you can just count the derivatives. So there's first order derivatives here. In principle, you can go forward and think about what would happen to second order with more and more derivatives. Okay? So you can start to recognize an idea or some incipient ingredients for an effective theory. Okay? So you have, in a sense, a controlled expansion in these gradients. So just for completeness, I'm going to write the J. The J has a term that has just the ideal part here, plus sigma I J. And then here, this is just isotropy, the fact that J has to be a three-dimensional vector. But the important part is, again, that you have the ideal piece, plus something that has derivatives, first order derivatives. You see, I'm using this stress tensor here. And here, you see, there's the gradient of temperature. If you put this equation together with this one, you find the standard Fourier law that says that temperature would diffuse with some coefficient given by here, this kappa is the thermal conductivity transfer coefficient, while eta is the shear viscosity, and zeta is the bulk viscosity. So, those are the equations. They look very simple, right? I mean, this is just, yes?
The term before that needs to be correct.
This one, yes, thank you, thank you, thank you, thank you. This should be I here, and J here, and then J here. Yes, and yes, we are not being very careful today, okay? It's just because, you know, I'm using the correct metric. The correct metric is signature, which is this. And some of my...
I think the question was, what carries the index I in this middle term with the
Sigma I.
No, sigma ij.
Oh, it's a matrix.
Sigma ij is a matrix, right?
It's
here.
not a sum, it's a sigma.
Yeah, sigma ij. Of course, I'm using Einstein's summation in this convention. Yes. And okay, so this looks simple, but it's not. This is a notoriously hard problem to solve, especially in 3 dimensions. And to the point that if you're able to say, to make general statements about the global existence and smoothness of solutions of this system, you get $1 million. Right? So this is probably the hardest way to make $1 million ever. But you know, there's a lot of stuff going on with the physics of standard non-relativistic Navier-Stokes fluids. Okay, but now you can start to wonder the following. What happens when the Knudsen number is not really very small, but it could be something of order 1? Can we find systems in nature where this happens? And it says yes, and I'm going to tell you here. And one way for you to see how the Knudsen number can be large is just that, so if this small scale is like the Newton path, so it goes like the density and some cross-section. If you keep decreasing the density, for example, you keep going far up in altitude, like for rarefied gases, like in an airplane, this guy can get larger and larger, okay? So engineers have to worry about this all the time. For us, I mean, especially for me as a theorist, this is sort of like this all lives in Gedanken space, but you know, this is a real deal. That's something important. Also, another example, which is pretty fun to think about, is something that is called a microfluid device. So these are things that happen, they're created in medicine. And basically the idea there is one that I saw is like this. Imagine that I have some little path, okay? And the typical size here could be of the order of 10 to the minus 6 meters. So this is like the typical size of this thing. And you have very big here blood cells, okay? And you have to talk about the flow of these blood cells across this little device. So, but the blood cells basically have the same sort of scale, basically. So for these things, the Knudsen number is of order 1. So this is important for those type of devices. It could be important for us, and maybe this will save our life someday. in one of those devices. But what I'm really interested in, and I think this is the vast majority of the people in my program, in the program that I'm participating, is really the frontiers of fluid dynamic behavior. And there are two trivial frontiers that I'm talking about here. The first one sort of follows this path of the microfluid device, which is the following. Remember, everything was about this small number, like the ratio between the micro and the macro. What if, even the big scale, we can make it as small as possible? Not even the size of an atom. Right? So this is an atom. The scale here is 10 to the minus 10. But this is an atom. But imagine that you go to the atom, and there's the nucleus, and you go to the nucleus. Sorry, this is the, I don't know how to draw an atom, but anyway. This, I guess a point for my scale would be good. So I have a point for the nucleus, 5 order degrees, 5 degrees of magnitude here, and then some electron cloud, something. So if you go from the nucleus, and now I can write a nucleus. I can draw a nucleus. So the nucleus will be this guy here with a bunch of little balls inside, and these balls are just protons and neutrons. So from here to here, you go from 10 to the minus 10 to 10 to the minus 15. Okay, that's the Fermi scale. But what if you see now, sorry, this is a mistake. I'm making the large scale become smaller than this, and even, and that's really outrageous, even smaller than this, just for the proton itself. Okay, so this is going to be, the order 10 to the minus 14, the large nucleus. So imagine, here, for the proton itself, can the proton itself behave like a fluid? In what regime could this be possible? You see, I shrunk this large scale a lot. So what does hydrodynamics look like for this? Okay. Large part of this program is towards understanding this. And the other frontier is not to the very small, but also to the reasonably large. And I can only talk about the things that I know more or less, and that has to do with neutron star mergers. Where now we are probing phenomena that are pretty interesting, because now we have strong gravity. Okay. We have very important parts in nuclear physics for the equation of state of this fluid, and particle physics for the different particles there and there. And we have very strong electromagnetic fields. And then you have to understand how you generalize all of this thing that you see. This is intrinsically non-relativistic as it's written here. How do you go from here to something that you can write down a TU or an energy-momentum tensor like this, that you can solve within general relativity? How do you do it? What do you have to change in relativistic fluids to make this happen? Okay? Yes.
In the first frontier,
Yes.
what is the? You didn't say anything about the small.
Yes. Yes. I'm going to talk about this, but normally the small scale here would be like something of the order of 1 of the temperature, which will be not that much different than the single, proton scale itself. So actually, there are 2 regimes that we'll see. We'll see one regime where we can make the system bigger, and there may be some separation of scales. But for sure, for this case, the type of physics that goes inside would be something of the order 0.1 Fermi, or even less. And then you have to really probe the intrinsic quantum, the color and fluctuations inside of your proton.
Should I be thinking about quarks, or what should I be?
Yes, of course, yes. Yes, exactly. So this is the physics of deconfinement. Whatever that happens, we are probing deconfinement not just in equilibrium, but really out of equilibrium, and that's the point. This is to understand the out of equilibrium properties of QCD. Okay? So I'm going to talk about more of this. Great. So let me first focus on the frontiers here in the very, very small, this has to do with things related to nuclear and particle physics. As you see, right, you could say that here, if you worry about the physics of the nucleus, you're a nuclear physicist. But for us, especially for me that I work in this field, I have to think about this. So there's really the intersection between nuclear and particle physics. The problem is intrinsically multidisciplinary. Yes?
We're saying QCD, but there I would have non-abelian symmetry, and I would only have covariant conservation instead of.
Oh no, for T mu nu is still fine, right?
T mu nu is okay.
Yeah, for T mu nu is still fine. Yes.
But for the color charges.
Yes, that is a very important question, because in order for this to look like a fluid, at least to have the hope to look like a decent fluid, somehow these non-abelian charges have to thermalize or become white fast enough, such that this, at least we have the hope to write it down. So in fact, one of the people in the audience, Uli here, was one of the pioneers trying to describe precisely this thermalization process. What happens to these non-abelian color scales. Okay, so now we're into QCD. And QCD, as you know, is the fundamental theory of the strong interactions. It tells us how the masses of everything that is, the vast majority of everything that is visible in the universe, how they get their mass from the interactions between quarks and gluons. And the relevant part for me here, since I'm talking about fluids, is to at least understand whether this would make sense, at least in equilibrium. Okay, so imagine that I'm in equilibrium, and if I'm in equilibrium, I would need to think about a pressure, so some equation of state. And luckily, after many decades, lattice QCD has provided us the equation of state of QCD, a finite temperature, and what we say, baryon chemical potential being equal to 0, so that means that we have as many quarks and antiquarks, okay, in your system. This is a problem that is as good as it gets in terms of precision. And so at least in equilibrium, things make sense. So, but how do we study the dynamics of the system out of equilibrium? Okay. So this is all computer simulations, right? So large-scale computer simulations in lattice QCD. But now, if you want to understand what happens out of equilibrium, you have to do experiments. And the experiments are called heavy ion collisions. And a lot of people in this program are talking about, they're members of the heavy ion community. And basically the idea is the following. We have to think about it, the whole problem of collisions, of colliders, differently than you would do for example, for particle physics. In particle physics, what do you want to do? You want to put a lot of energy in some small region so then you can excite things that have a lot of mass, like a Higgs. Here is different. You still have a lot of energy, but you want to distribute this thing out such that you want to see how the energy and the momentum flow in the system, and how you hit the vacuum the right way to actually see these quarks and gluons and how they flow in your system. Okay? So these ideas go back a long way to Kavli and many others. And now I can schematically draw what happens in heavy ions in the following way. So what happens, you use some large nucleus, for example, gold or lead. Okay, so there's gold or lead, okay? And you accelerate them, and you collide them with very, very large speeds. So for example, the gamma factor, that would happen, for example, in the LHC, the relativistic gamma factor would be of the order of 1,000. Okay, so they come with very, very large speeds. These, they come in like this way. So imagine that this is the collision axis, like the z-axis, okay? So these things collide, and something happens here, because you have to go from the original nucleon degrees of freedom of the protons and the neutrons into something else, which will be quarks and gluons. This happens at a very small scale, even smaller than the time that it takes for light to go across a proton. So this, the time scale that it has to do with this is of the order of 1 Fermi over c. So from here you go from a confined system to a system, now I'm going to call it QGP, So this is the quark gluon plasma, where now the degrees of freedom are deconfined quarks and gluons. It doesn't mean that they're weakly interacting yet, because the temperatures are not very large. The temperatures could be of the order like 500 or a little bit higher MeV. Okay? And the mass of a pi is of the order 130, 140 MeV. So this system produces this QGP, so now you have deconfined degrees of freedom. The temperatures are very large, so that's why you don't see the nucleons anymore. Then, as any decent system, this thing is expanding in the vacuum, so it cools down. As it cools down, it gets larger and larger. And then at some point, and this is where the whole thing enters, the description of this, the whole dynamical process is done via relativistic fluid dynamics. How you start from an initial quark-gluon plasma with deconfined degrees of freedom, and how this energy, momentum, and baryon number flow across space and time until the temperatures are low enough. The temperatures are lower than, let's say, the pi mass. Okay? Then your system now starts to hadronize. So you go from deconfined quarks and gluons to, again, a bunch of other protons and neutrons and kaons and many other particles that are produced and eventually observed in the detector. Okay? So that's how you talk about QCD out of equilibrium in the lab. Now, this is really a system with many, many properties. The temperatures are very large, so just for you to get an idea, like 100 MeV, or the pi mass, is of the order 10 to the 12 Kelvin. So this is a very, very hot thing. It is also very small, because this size, and think about this now as like the transverse size. So Z is the beam direction, and this, when they collide, they have, this is what I'm writing here. So this is the transverse part, okay? They look like pancakes because of Lorentz contraction, okay? It's a very highly relativistic thing. And then, of course, the whole thing is to understand how you model this. How do you consistently model this, and how you compare to data. So phenomenology and the input from experimentals and how you talk to experimentalists and theorists is fundamental in this field, fundamental. The very observables are completely new, and it had to be defined as you go. Yes?
Is it clear a priori that there should have been enough equilibration to be able to do certain things?
Fantastic question. That is literally my next point. Because the first thing that you should say is like, I don't believe a word of this. There is nothing that could be more complicated than this system. This is a system that is known a billion. And not only that, there's also a billion fields, right? So the quarks have electric charge, right? So not only you have very strong color fields, you also have very, very strong electromagnetic fields. In fact, estimates, depending on how you collide, if it's non-central or not, can give you some magnetic field that could be larger than 10 to the 18 Gauss. So it is also electromagnetic plasma. So how does that work? Yes, so at first you should say, yes, I don't know how I can believe this. Well, let me give you a little justification, and then I will remove it completely. That will make you more confused. But don't worry, being confused is the point. That's why we are here. In fact, a lot of people in our program, including me, we are very confused about how hydrodynamics actually works in these systems. So, let's go to this point. So let me first tell you a few things that have been learned over 2 decades. There is intense theoretical and computational effort and phenomenological effort, a lot of discussion between theorists and experimentalists. And just like you had before, you would have some coefficients. You would have an equation of state that we get from the lattice, and then you get some transfer coefficients. Transfer coefficients are very hard to compute because they describe real-time phenomena. So normally what you do, you try to extract them by comparing numerical simulations to data. And what has been found, this is sort of the state of the art at this point. I can write down, let me define these objects first. So again, I am using dimensionless variables. So temperature is in GeV. So the temperature of these collisions basically run from here, from 0.1 or to 0.5 GeV. And what you see from comparison to data is that this quantity, the shear viscosity, the same thing that you saw before in the other fluid, divided by S, which is the entropy density, then in these units is dimensionless. This is constrained by data to be within this regime. Okay, so these are many, many, many simulations. This involves the whole framework of Bayesian inference analysis. It's a very sophisticated simulation. And what we see is that this system has a very small shear viscosity to entropy ratio, very close, in this sense, to the famous 104 pi that appeared out of ADS-FT calculations. That goes back to Kaufman, Son, and Sternes in 2005. Wow, this is a long time now. Yes?
What is the numerics actually doing? Is it doing the equivalent of kinetic theory, or is it trying to solve Hydro equations?
So yeah, so what they do, they solve the Hydro equations,
Okay.
and they compare the predictions from the Hydro equations to data. So basically, you see this part here, when they get code, they start to produce these hadrons. And basically what the experiment does, it counts how many hadrons you see in a given direction with a given mass. So, you know, if it's a proton, if it's a pion, and then by this angular distribution, you can infer what the viscous properties are.
And the Hydro equations are taken from the equilibrium densities equations?
No, so the Hydro equations, yes, so this is, I'm going to mention this a little bit later. So there are specific models that try to solve this, implemented these relativistic corrections. But I'll get to that.
So in this kind of
Yes.
hydrodynamics, what is the meaning of the number conservation equation, the first one that you put down, the continuity equation?
Yeah, so
what
you
is
still,
rho there?
yeah, so you
This
still
is the
have
initial stage.
yeah, you still have baryons. I mean, baryon number is still conserved, but precisely for the ones that I'm interested in, for the very, very large energies, on average, you produce a system that is basically symmetric with respect to quarks and antiquarks. So you don't necessarily need to follow the dynamics of the baryon current itself, but its fluctuations become important when you measure. So for example, if you have some fluctuations of baryon charge, you can see that experimentally. So, but there's another regime that I'm not going to talk about here because there's no time. But when the collisions are not so energetic, imagine that you reduce the center of mass energy of these collisions, and then these nuclei, instead of just passing through each other and disturbing the vacuum to create these particles and gluons, what they do, they sort of get stuck. As they get stuck like this, the energy is smaller, then baryon number becomes an important thing that you have to keep track and actually solve together with the equations. And I'm going to write down very soon what the equation looks like for the baryon current, for example.
You cannot count quarks, right?
No, you don't count quarks, yes. But you could still count, baryon numbers, charge, and stringent. Stringent is actually it's a good quantum number for these collisions.
But those are non-abelian charges, so they're...
No, those are global. Those are global. Those are not non-abelian. They're abelian charges. Like baryon numbers are abelian. Yes. Okay. So, but now let's go to the question, right? How come? How come? Well, how could this system behave like a fluid at all? Well, let me tell you a little bit of the history. People have been working on this for many, many years, and the models, of course, get better and better as a function of time. Especially this transition, this is like the hardest part, how the system goes from the nuclei to the deconfined matter. So there's a lot of modeling involved. And at first, if I go back more than 10 years ago, around 2010, I can draw more or less what the energy density of your system would look like in the transverse plane. So remember, the collisions are in the Z, and this, you collide with this, so that they start to evolve like that in the transverse plane. This is X and Y. And if you were to draw this, back in the day, the models would say that something was really kind of like this, very, very smooth. Okay? To the point that it was so smooth that relevant gradients in space were of the order of the radius of the nucleus. For example, gold or lead nucleus, which is of the order of 5 Fermi. Okay? So if this is now your big scale, okay, and if you use that 1 over the temperature basically is this sort of microscopic scale in your system, and in the temperatures of the order of 200 eV, if this is L, you can estimate that your Knudsen number, which is L over little l over capital L, will be smaller than like 0.1, 0.2. So, it looks nice. It looks kind of reasonable. Maybe, hydrodynamics makes sense because, this is not very, very crazy and it's kind of smooth. Okay. But, as anybody that worked in the field in this decade would now appreciate, nature turned out to be much more interesting than the models. So what we now know is the following. You see, think about this. The nucleons inside here, they are not little billiard balls, right? They're really quantum mechanical objects, right, that have quantum mechanical fluctuations. And just if you think about the size of a proton itself, like a Fermi, then you should have a lot of structure at different scales from the beginning, from the initial state itself. So it turns out that initial conditions are not so smooth as they used to be. And in some models, and people can discuss the physics of these models, some of these things will be kind of like this in the initial state. You would have large peaks and valleys for the energy density, so the gradients will be large, which means that, in general, you would not expect that this Knudsen number is very, very small already in the initial state. Okay? Another thing that is interesting is that as the system expands, there are kinematic constraints that tells you that the gradients in the longitudinal direction along the beam pipe are very large at very early times. So the Knudsen number is generically does not need to be small. Yet, hydro works. It works in the sense that you have these models, you have the whole phenomenology set up, very sophisticated things, and you compare it to data, and it still works. Okay? And of course, you start to get interested and nervous, like, okay, but why is it working? Well, experimentalists are normally more clever than in theorists. So what they do, okay, let me make this even worse for you. I'm going to decrease, instead of having a very large nucleus, I'm going to make a tiny one. For example, a deuteron or even a proton. So what happens if now you have proton collisions? Then you have to create initial conditions. Now you really have to talk about the substructure, the sub-Fermi structure of these things, right? Because the Fermi itself is like a Fermi. Then you run through the whole machinery, and in some limits, basically in the limits where you have very, very large number of particles, we call it a high multiplicity regime, we actually find that to a good degree, hydro works. Works in the sense that observables predicted from this framework look very similar to the ones found in the experiment. Okay? So, we are now trying to understand this. This is one of the motivations for having this workshop, is to understand how come, as you keep decreasing the size and changing all the different parameters that you could have in heavy ion collisions, how come that this whole hydrodynamic framework still works? Is it because maybe the data is such that it's just too general, it's just energy momentum conservation, so if you do anything that conserves energy momentum, you'll be fine? Or it's, which I think is I don't think it's this option, I think it's the latter, which is that perhaps hydrodynamics is more interesting and more complicated than we thought. So there are many questions that appear here. So this goes into the surprising effectiveness of hydrodynamics in heavy ion collisions. Okay. This is a play with words here for the famous thing from Wigner about the surprising effectiveness of mathematics in physical sciences. So we are trying to understand that. How could that be true? How do you derive or systematically define hydrodynamics in a complicated system where the underlying physics theory is QCD, something non-abelian that has non-abelian charges and stuff like that. And also, look, this actually is pretty interesting. As you keep decreasing the system, the flow, in all of this heavy ion collision, the flow is relativistic. So the velocities involved really are close to the speed of light in some parts. So we have to use relativistic fluids. So this gives us the opportunity to think about relativistic fluids. And as you keep decreasing the system, it actually gives us the opportunity to something else, is to understand something very deep, which is the fluctuation dissipation theorem. So if you remember the fluctuation dissipation theorem, you should just think about the Langevin equation. So you have something like this, some force, some little particle that has some viscosity here in the presence of a stochastic force, and the amount that the stochastic force fluctuates goes with the temperature and how much it dissipates. But now we have the opportunity to understand what happens to this system as you keep making the system smaller and smaller. If you have dissipation, you should also have thermal fluctuations. How does that work in relativity? Okay, so this is an experimental thing that can be done in this system. So, now, if I can write down basically a big picture point of view, one could write down something like this. Let me write some phase diagram of fluids in a very, of course, biased way towards my view. But it's like this. Imagine that here on this axis is quantumness. So this is something, of course, is 1, but you know, let me put it here 1 here. And here is velocity. And you know, the speed of light will be here as 1. We live, most of the time, we live here, where the velocities are very, very small, and h bar doesn't matter so much, right? So we are here. So this is KITP. But not the physics of KITP. But now, for example, here, very non-relativistic and very quantum, we can think about bosons and condensation in these atomic gases. Okay, so we have several cool examples there. Here, when you're very relativistic, okay, and as you keep decreasing the size of the system, quantum effects have to start to show up, right? At some point, you have to understand that the proton is a confined thing. It has, you know, QCD confinement there. How do you deal with this? So as you keep going from, let's say, lead to something so small like a proton-proton, you keep going up this ladder here with something very, very relativistic and extremely, extremely quantum. Now, you could spend, of course, a lifetime on this plane, and there are many other type of axes that it could define.
You should stay to the left side.
We should stay, yes. Let me see, I have 5 minutes. What I'm going to just mention to you now is what happens as you create another axis here, which is now we are probing gravity. So imagine that you're not just talking about things like this on Earth, but things that have very strong gravitational fields, like neutron stars and matter falling into black holes. So this is the second frontier, the astrophysical frontier. And I have just a few words that I can mention there. You please ask me afterwards if you have other questions. So the point is the following, that how do you combine fluid dynamics and general relativity? How do you generalize these Navier-Stokes equations in a way that you can now do the following thing? We could say, oh, I still have now energy and momentum conservation. Okay, so this is the energy momentum tensor of the system, describes all the energy and momentum distributions. I have, for example, some baryon current or some other conserved current that you have. Okay? And of course, this comes from this one. I want to make sure that all of this can be done systematically and correctly using Einstein's equations as well. So I want to make sure that I know how to do this whole process of the coarse grain. How do you go from equilibrium to out of equilibrium? How do I create consistent models that I can put in here? And I still can guarantee that space-time is well defined. It's a globally hyperbolic space-time. There's a Cauchy surface you can solve. You know, you can understand the future starting from the past. But why is this so challenging? It turns out that it's very challenging. Okay? People have been thinking about this, of course, for many years, starting in the 1940s. Okay, so Eckert and then Wendell Lifshitz were the first people to think about this. And this is very, very challenging because if you just try to generalize those theories that I had here, the ones for Navier-Stokes, where you have a simple relation, right? So you have something like this, which was a derivative of the flow. Now you write a covariant version of this. This will be something called a shear stress tensor, like this. And this will be written like this. Let me put here, there's some projectors here that I'm going to talk about, but it will have to be like this, where u mu is now a 4 vector, like this, and u mu is a time-like normalized 4 vector. If you try to do this, you plug in things like that, just for the standard generalization of these existing theories, you try to put it here, it does not work. It does not work. It will not give you something that you can use in general relativity. In fact, for these type of theories, precisely with this thing here, the problem, we say technically, is not hyperbolic. As it's not hyperbolic, you lose the initial value formulation for your system. So you need to fix it. In this workshop, there are many different theories, and basically we have specialists of many different approaches to try to solve this. I work on one of them, and actually I work on probably all of them. But there's one that I like the best. But this will take too long to explain. What I want to say now is that recently there have been many developments to actually prove and try to find well-defined theories where all of these properties are preserved, and you could still have a well-defined formulation in general relativity. So far, in fact, we have a formulation where one can just prove everything you want. You can prove that the equations are causal, that the equilibrium state is stable, and you can solve it, for example, dynamical problems in general relativity, and so forth. In fact, one of the motivations for this program is understanding the properties of such theories and how we can use them in other applications, for example, cosmology and so forth, and neutron star mergers. So, just to finalize, let me make just one little diagram. So, over the course of this short talk, I told you about the excitement that appears when you do relativistic fluids and the different areas that you can connect, ranging from neutron star mergers to heavy ion collisions and many other fields. So if this is our KITP program, there are many different types of areas that connect, and they are represented by people from different fields. So we have nuclear physicists, people that do heavy ion collisions in the quark-gluon plasma. So this feeds into the KITP program here. Just to give an idea of what kind of people we're here, we have people that do experiments, and they are very connected to data, experiments and phenomenology. So we have specialists on that kind. We have people, we have mathematicians that try to understand all of these complicated properties of nonlinear PDEs. People talking about math of PDEs. We have people talking about asymptotic properties of series and resurgence. We have, of course, people working on GR, general relativity, gravitational waves, numerical relativity, and the connection between this and neutron star mergers. In a given week, we'll have people from all this. Of course, we have string theorists, have string theory. You know, a lot of developments concerning hydrodynamics came from investigations using the ADS-FT correspondence. We have a specialist here. We have, of course, people that just work on effective field theories, either in condensed matter or also in particle physics. Just QFT in general, trying to understand these phenomena from quantum field theory. Have numerical simulation people. Numerical simulations, and they use large-scale, big data sort of thing to understand and describe this type of physics. And of course, we also have a lot of people working on relativistic kinetic theory. This is very important for this type of physics. And I guess that's more or less what it is. So please, if you have an opportunity to talk to the participants, it'll be great. I think you'll like the discussions. Thank you so much.
More questions?
Yes.
Yeah, so, I mean, I think of, hydrodynamics is defined by that kappa number being smaller, much smaller ones. I don't really understand, like how, step one, what do you do? I mean, you can do numerics, but like gradient expansion breaks down, so like what?
Yeah, so, okay, so this is a great question. And in fact, we are, as you see, we're very worried about these questions. And one of the things that came out from this field is precisely to understand the properties of the gradient expansion itself. So by gradient expansion, it's the same as this Knudsen number expansion. We're just putting more and more derivatives to describe the dissipative quantities. And one of the things that we were able to answer, at least in certain cases, is whether, for example, this series actually converges or not. Because it could be that, for example, if the series converges, maybe, Kn doesn't need to be very, very, very tiny. It could be a little bit larger, but it could still make sense out of the formalism. And we now understand certain criteria where this series will converge, and we also have examples where it does not converge. And if it doesn't converge, what do? Just like in quantum field theory, normally you expect that amplitudes or physical things go with some powers of the coupling, and then if the series diverges, which is an asymptotic series, which is normally the case, you have to worry about it. What do? You resum. And then as you resum, you get new things. For example, instantons. Right? So instantons will be things that will never show up at any order in the coupling, in the small coupling, because they go like this. These things appear here too, in very specific models. Very specific. We don't really understand too much. But we see that if you describe, for example, these dissipative quantities like this, if this series diverges, we see that there are some other things that will go like this, when the Knudsen number is small. These will be associated with things in the field that we call non-hydrodynamic modes. And one big question in the field is how you take into account those things in a consistent way, and how they actually influence what happens in your system as the Knudsen number is not small. So the short answer is we are aware of this and we are working on it, but it's a very complicated problem. So there are people, for example, in my field, in this field, that will say, no, hydrodynamics is a small expansion in gradients. Anything that is not there, we just call it non-hydro, and then you do something else. And there are other people that see these particular examples and try to extend further and further what they think about hydrodynamics. So, in fact, the fight between those people has been very interesting during this week. Very professional, everybody very happy, but it has been very interesting. But yeah, so we're thinking about it.
When you say that hydrodynamics is unreasonably effective, how effective are we talking about? So, what is the error?
Well, okay, let me tell you the following. Of course, I'm going to consider a very good system, but you see, so you're sitting close to the person that works on this much more than me. Let me just entertain the answer the following way. So there are these some observables that we call flow. They're called anisotropic flow. But at this point, the only thing that matters is how many of these particles come in at a certain angle and what type of particles and with what energy. Okay. So people have done a lot of simulations, and they tune the parameters, and they get the model working for certain systems, and then, indeed, they made predictions. There was a nucleus, the xenon nucleus. It's an interesting nucleus. It has some interesting properties in terms of nuclear structure itself. It turns out that this guy is not really spherical, at least not the version that they use, the isotope. It's not really spherical. It has a very tiny deviation. But actually, experiments in nuclear structure didn't know how much this deviation was. So people did the simulation in Hydro. They did the calculations. They made the predictions. And the predictions worked within 1%, or more or less, right, Willie?
Well, I would say 10%.
No, for this one, the particular prediction for the xenon, I think is more. You see, the disagreement is starting already. Yes. For the xenon, I think it was better.
If you have a Knudsen number of 1
yes.
and expect errors of order 100%, I think 10% is
yeah, exactly. Okay, so that is the professional phenomenologist way to answer. Yes. So it works really well. Much more. I mean, you would expect it would just be nonsensical. No. Very, very, very good. Again,
Let's stop right there
Okay.
while you're ahead.
yes.